Hi everyone, so we are going to discuss example problems of undecidability and intractability. First off, we have undecidability. Example problem is the word problem given a string input of three symbols A, B, and C.
Suppose we have three equations. BA is equal to ABC, BC is equal to CBA, and AC is equal to CA. Given a string BAC, we can replace BA with ABC, so it now becomes ABCC. We can replace BC with CBA, so it now becomes ACBAC. We can replace AC with CA, so it now becomes ACBCA. So basically, it will just continue substituting since for every substitution, there's a possible string belonging to this set of strings.
Given the string BACABCA, one might ask if we can deduce for the three equations that it is equal to ACBCA. To prove it, we can use substitution. So we replace AC with CA, so it becomes CABCA. We replaced BC with CBA, so it becomes CACBAA, and so on. As you can see, we can obtain many other equations by substitution. It will never stop if modeled by a Turing machine, since it will continue to substitute, thus making it undecidable.
Next, we have intractability. So for intractability, we have certain cases in which the runtime of an algorithm is not that optimal or efficient. And for this example, we chose traveling salesman for intractability. So the traveling salesman or the traveling salesperson problem is one of the most common examples for intractability because basically it runs on a big O which grows fast. And within this example, I will discuss on why the traveling salesperson is indeed intractable. Now let's get further to our example. So for our traveling salesman problem, given a weighted graph G, we will find all possible Hamiltonian cycles. But first, let's recall what a Hamilton cycle is. So a Hamilton cycle is a cycle in which every node or vertex is visited once. So soon, we will find all possible Hamiltonian cycles that will be the shortest path for the traveling salesperson. So for the next examples or the next papers, we will be given a graph, a weighted graph in which we will find all possible Hamiltonian cycles. It is a complete graph because basically the traveling salesperson will execute on a complete graph. Now let's go to our example. So we already have a graph G in which it is labeled A, B, C, D, E for its vertices. So it is complete and weighted, and our goal is to find the least path. So it will take big O of n factorial, and as we can see, big O of n factorial is not that efficient for an algorithm because it is not polynomial timed. So what will happen here is that it will grow faster than other polynomial time algorithms. So for example, we have n raised to 4, n squared, n cubed. Thus we can say that this is not that optimal, or it is very impractical to use. So in finding all the possible paths that will be the shortest or the least cycle, we will try all possibilities in the graph. So we have these weights for the corresponding graph G. So we already know that our traveling salesman problem will take big O of n factorial, but the real runtime of the traveling salesman problem is actually n minus 1 factorial over 2. So for example, we have A, B, C, D, E as our first choice. So this will be there will be 5 vertices for trial. So we have CTA first. So after CTA, it will never be taken again. So we will take B, C, D, and E. So this will take factorial until we find the least possible weight that is a Hamiltonian cycle. So we visit each node and all the weights. This will be optimal for smaller graphs, but what if we have a bigger graph? Let's say we have a graph with vertices of 20. So this will not be optimal, and this will take a series of steps which are quite large. So it will be very, as we can say, impractical.